Hey folks, welcome back. I am here and it's time to add some thrust to our simulation. Um, we did projectile flat earth, then projectile like Newtonian gravity, and then we made it 2D. And so the last couple things we need to add are the thrust model and aerodynamics. So I'm going to do thrust. I want to do a two-stage rocket. Um, I don't know how far I'm going to get in this video. Either I'm going to do the first stage in this video and then the second stage another, or if it doesn't take too long, I'll do both stages. It just like kind of depends. I do all my videos off the cuff. I don't really prepare very much for these. So here we go. The first thing that we need to do is add thrust to our simulation. So what I'm going to do then is I'm going to add a thrust model, and I'm trying to think how I want to do the guidance. Um, I think for right now, I'm just going to do open loop, in which case there's not going to be any guidance, if you will. So it's just going to be based purely on time, which is not how you should do it. Really, if you are, even if you're playing Kerbal Space Program, you shouldn't just like close your eyes and hold a stopwatch and then fire different stages at certain times. You should wait till you're at a certain altitude and your apogee's at a certain point and then fire. But I don't really want to deal with all that guidance, so I'm just going to kind of do everything open loop. And I'm pretty sure that the code that I built last time was just open loop like that. Okay, so I'm going to save this as, it's not a projectile anymore, it is a single stage rocket. Okay, so that's what I'm going to call it, single stage rocket. Alright, so def thrust with time as the input, and now I need my equations for thrust. So my thrust is going to be my, I want an if statement here that basically says like if t is less than, let's just say 40 seconds, my thrust is whatever my max thrust is. And I guess what I'm going to do is like, here's my rocket, right? So my max thrust, so if I have a 640 gram rocket, I feel like 50 newtons of thrust seems pretty realistic for a rocket. I don't know what thrust to rate ratio that is, but I'm sure it's pretty big. And then these hobbyist rockets, I was actually just thinking, they only have like a 5-second burn time. Otherwise, I'm going to make my thrust equal to 0. Now, here's the other thing. I need an X force. Oops, I hit Alt on accident. Whoops. I need an X force, and I need a Z force. And I forget, is Z along the surface? Alright, so I mean, I realize it's been one day. Let's see, what are my initial conditions? So my velocity, oh, I'm in orbit. So here, let's say this is for orbit. And then, can I do block comments in this? Yeah, I can, sweet. So I can do, so then we're going to do, let's see, initial conditions for single stage rocket. Okay, so x0 is still going to be our planet, and then z0 is 0.0, but then my vel z0, so this was basically going up. So x is out of the board. Is that how it works? Why did I give my velocity 100? I didn't really need that, did I? Probably not. Let's comment that out real quick. Let's see what's going on here. So I feel like I didn't need that. So let's run this. And I'm in orbit. Cool. Oh, I think I was just kind of messing around and saying like, hey, if I was like right on the surface, like I need to be 600,000 kilometers above the surface. And there we go. That looks good. Okay. All right, so let's make that a block comment again. And then I'm on the surface of the planet. I'm not 600,000 meters off the surface. And then, so my vel 0, actually my velocity for both is 0. But I'm just trying to understand what the different axes systems are. So I'm going to make my thrust x, yeah. So I'm going to make my thrust x, my max thrust, and my thrust z 0. And then here I'm going to make my thrust x 0.0 and my thrust z 0.0. And actually, I think I'm even going to make this a little bit more complicated, believe it or not. I'm going to just call this thrust F, like this, and then thrust F, let's see, thrust F is 0.0, and I'm actually going to make a theta variable, and for now, so theta is going to be the angle of my thruster, and so if I make it 0.0, then my thrust X is going to be thrust F times the, I'm going to do cosine of theta, and then thrust Z is thrust F times NP sine of theta. There we go. And then I'm going to return np.asArray thrust X and thrust Z. Okay? So that should be good. So then down here, when I call my thrust vector, I should just be able to call the thrust function with T. R0 is not defined. Oh yeah, I compute my period here. So this is for the single stage rocket. So maybe can I move this into my block comment here like that, and then make a period here equal to, I don't know, 25 seconds, and then run that. And so let's see. Yeah, it looks like I don't have enough precision on the planet, so it doesn't look like I'm actually on the surface. So let's make 1,000 points for the planet, and then let's zoom in here. There we go. Okay, so I'm definitely on the surface. Now, what really matters for my rocket is the altitude. So 50 newtons must have been insane. Let's just do a quick calc. So if I do 50 newtons divided by 0.640, it's a thrust to weight ratio of 7. No. I'm sorry. I have to do 0.64 times 9.81. That is the mass of my rocket. And if I do 50 divided by 6.2784, I've got a thrust to weight ratio of 8. So let's crank that down to 20. Is my insert key on? That's what's going on. All right, and let's launch this again. So I don't really care about the planet orbit. I care about this one. Okay, so this one makes more sense. So you can definitely see the rocket is like slowly accelerating before it goes up. And then here's the velocity. This kind of climbs. And it looks like I collided with the... No. That's not what's happened. This is the total speed. So I'm plotting... That's total speed, so it's always positive. Is that right? Velocity is vel out. Yeah, so it's always positive. So this is apogee over here at 15 seconds. Okay? So you might think that the video is over, right? Because I did it. I did my first stage. But the problem is that I'm not actually simulating the change in mass, right? So I need to put in here, you know what I didn't do, which is bad practice, is I forgot to make this a global, my max thrust. It looks like everything's fine, but I still want to make sure I have it in there. So I need an ISP for my rocket. Now I'm going to just assume that it's 200 seconds. I don't actually know if that's true, but I'm just going to do it. And so when I run my thrust model, not only am I going to return my my thrust force, I'm also going to compute my m dot. Now m dot is equal to my thrust force divided by my exit velocity. And my exit velocity is my ISP, so I need to make my ISP a global variable. And oh, by the way, thrust needs to be negative. Sorry, m dot needs to be negative because I'm losing mass. And VE needs to be ISP times the surface gravity, which I'm pretty sure is 9.81. Even for, well, if you have a rocket on another planet, it doesn't really matter because I'm assuming that at least in this epoch, you know what, if you're watching this video 1,000 years in the future and the ISP standards have changed, so be it. But at least as of right now in 2021, the ISP standards say that you use the surface gravity of Earth. And so the exit velocity in meters per second is 9.81 times ISP. Okay? So down here in the code, I need to grab m dot. Now, let's just make sure this code still runs and everything's still good. But now what I need to do is I need to put m dot in here. Now that means that I actually need to add a state. So that means that my mass is not a global anymore because it's actually going to be a state vector. So mass is part of the state vector now, which means that this mass up top is no longer mass, it's mass 0. It's the initial mass. Okay? So, where are we? So we've added mass as a state. We've computed m dot. So I'm going to call this like the propulsion model because it's not really thrust anymore. We are computing the m dot, and then m dot looks good there. And then now we need, in the initial conditions, we need mass 0. And I think that should work. I want to plot mass as a function of time. So that'll be mass out is state out of all comma 4. And then I should be good. I should be able to just plot mass. And so I've got plt.figure. Am I losing my voice here? This is terrible. I was screaming a lot at the beach today. Mass out, pltx label, time in seconds. And then plt.y label, which is mass in kilograms. And then plt.grid. All right. Let's check this out. Let's see if we don't blow it up. PLT is not defined because, of course, I can't type. And let's look at our mass. There we go. All right, we lost some mass. Sweet. In 5 seconds, we lost some mass, and everything is good to go. Now, I think we need to put in an if statement in here. Like this 5 seconds, I think we need to have MECO. That's main engine cutoff. So I'm going to put MECO, and I'm going to put MECO, like that. And here's my rocket, right? So MECO is 5.0 seconds. Now let's say for kicks, you're like, oh, I'm going to burn my rocket for 20 seconds. Well, I'm willing to bet, oh, okay, I guess my ISP is really high, so I'm not burning that much fuel. What did that do to our altitude? Oof. Oh, wait, that's total speed. Yeah, so this is crazy. You notice that the velocity increase is not constant because we're losing mass. We're actually like accelerating faster. And it looks here that we're still climbing at this point. So we need to simulate longer. I kind of want to put all my stuff up here. I don't like that everything's like down in here. So I'm going to pull this out and put this up here and say my rocket. There we go. Initial conditions for single stage rocket. And then I guess I'm going to put, I'll put parameters of rocket like that. And then throw this in here. And then that way I can kind of change everything just by looking at one part of the code. And so my period is now not 25 seconds. Let's try 250 seconds and see what happens. Okay, so what altitude did we get to? It looks like we got to, what, like 21,000 meters above the surface? Okay, so then the question is can we get to orbit with this thing? And I don't, well, I mean, I say we can't, but we can just make up a rocket, right? So let's just make our rocket like really efficient, right? And let's see if we can just make this up. Okay, so everything kind of blew up. Let's make it 10 kilograms and see what happens. Okay, there we go. What is our altitude here? All right, but let's just make us have like more. I'm just going to have a ton of thrust. But see, this is where things get weird, right? Like, I don't even know what happened. I gave my thing like too much thrust. But what happened to my mass? Let me try this again. So what happened to my mass? Is that mass, figure 3? Yeah, okay, so if mass, so if you increase the thrust, you increase your m dot, and if your mass goes negative, so I'm going to say, let's see, maybe here. If mass is less than 0, then, here, let's do this. If mass is less than 0, well, greater than 0, hang on, greater than 0, then dd dot is force divided by mass, and otherwise, dd dot is 0, and m dot is also 0. Otherwise, the whole simulation just blows up. So it looks like it still blew up, kind of. Yeah, mass went to 0, and then basically everything else just kind of, freaked out. And our altitude did something weird. But basically, this rocket doesn't work. Okay, so what we need to do is find a rocket that works. So, like I said, I've done this before. So this is a suborbital flight. So let's put all this stuff into the code. So the mass in tons is 5.3. Holy mackerel. Okay, so the mass is, let's see, so I'm going to say mass tons is 5.3, right? So that is, so the mass 0 is the mass tons. Well, that's like weight tons, right? Weight tons. You take the weight in tons times 2,000 pounds, and then you divide that by 2.2, and that gives you the kilograms. Okay? The thrust is 167,000. I think that's in kilonewtons. So that's 167,097. And by the way, these are, these are Kerbal Space Program values, aren't they? So we need to simulate on Kerbin. So I don't actually know, like, I'd have to look up, like, how big the Saturn V is and things like that. But that was why I put these comments in here, so I can just change us to Kerbin right away. Okay, so there's, what time is MECO? So MECO is 38 seconds. 38.0 seconds, so that's main engine cutoff time. What's the ISP? It's 250 seconds. Okay, and I think that's everything that I need. So let's give that a go and see what happens. So I shot straight into the atmosphere. Okay, boom, there I am. It looks like I'm like, let me look at my altitude. So there's my altitude. Oh no, sorry, that's meters per second. So I'm 1,600 meters per second. Keep in mind, I don't have drag or anything on this. And it looks like I'm hitting, okay, if I add in drag, that'll probably come down. I just want to get to orbit, so this looks good. 175 kilometers. Let's simulate a little bit longer. So let's do like that's the ISP, I'm sorry. 250, the period. So I'm going to do 500 seconds. And there we go. Okay, cool. So I went up into the atmosphere, and then I came back down, which is kind of cool. Let's do something kind of weird, wonky. So my theta is always 0, so I'm always angled upwards. Let's give it an angle of like 10 degrees times pi over 180. Okay? And let's see what that does to my, that looks cool. See, so I've angled sideways, right? So I've like fired, angled or whatever, and now my trajectory kind of looks like this. So I'm definitely suborbital because I came back down. I did not get into orbit, but I definitely left the atmosphere. I haven't coded in the atmosphere model yet, but so be it. So I don't know how long this video is. I don't really want to check, but I kind of want to add in the second stage. So we burn for 38 seconds, but it takes 260 seconds before I fire my second stage. this is where things get kind of weird. When you fire the second stage, you lose your entire first stage, right? So there needs to be a time where, let's see, this logic is going to get kind of awkward. So timing for thrusters, okay? So if t is less than Miko, I'm going to compute, let's put exit velocity up here. Actually, this is a constant, so I can just put exit velocity like up here. Well, here, let's put it down at the bottom because I never need to edit it again. Yeah, like kind of with the initial condition vector. So compute exit velocity, and then here, populate initial condition vector. All right. And then I need to make exit velocity a global, which I did. Okay, so timing for thrusters. So if we're in here, we are firing the main thruster, okay? Angle of my thruster, and then m dot. Now what I want to do is I want to put m dot in here. Oop, I didn't grab the x. Okay. So we're firing the main thruster. If we are, and let's do this. Let's say if t is less than t Miko and t is greater than t Miko and t is less than, I'm going to do t Miko plus separation 1, t separation 1. Okay, so what that means is, how long does it take you to separate your first stage? Okay, if you're doing that, the thrust is 0, but the m dot is, and this is where things get weird, I need to lose the mass of my first stage in TStep seconds. So, okay, so let's do this out. So I want my mass lost to equal the mass of my first stage, right? And that needs to happen, I'm thinking of like a rectangle, right? So the length is TStep, and the height is the variable that I'm solving for, and the area is the mass. So if I take the mass divided by TStep, so my m dot is the mass divided by TStep 1, and it's negative. Okay? And then if t is greater than t Miko plus TStep 1, my thrust F is still 0, and my m dot is also 0. Okay? Let's see if that works. TStep's not defined. Okay, I'm going to say that TStep 1 takes 2 seconds. Length of time to remove first stage. Okay, and then how much does the mass weigh? The mass of the first stage. Do I have that in my other code? So here's where I make an orbit. Oh no, that's just like, okay, here's my 2-stage rocket. See, mass in tons is 5. Do I not simulate like dumping mass in this code? Let's see. It doesn't look like I do. So on a 2-stage rocket is 5.3 plus 2, and I'm burning. I'd like to lose something. Let's just assume it's 1 ton. Okay? So mass 1 tons is 1.0. I guess that's fine. And then, so mass 1 is mass 1 tons times 2,000 over 2.2. Okay? Let's see if that works. So here's my mass. Oh, it worked. This is awesome. Okay, so basically maybe it's hard for you to see, but this is the first stage where we burn, right? So we're burning the first stage, and then we drop the first stage. And then now what we're going to do is we're going to coast to 260 seconds, and then we're going to burn the second stage, okay? So I'm going to do now, oh crap, this is a single stage rocket. Okay, so I'm just going to leave this here. And then I'm going to file save as, and I'm going to call this, I understand that my figures are ready. Okay, thank you. And I'm going to call this 2, double 2. I'm going to call this 2-stage rocket, okay? All right, so now I have a different code that I can, so you can tinker around with that first code. All right, so we've dropped the stage. So now what we need is T2 start, which is the second stage burn time. And I'm going to say we started at 260 seconds. And then, yeah, see, they're doing 100, they're saying 150 seconds, and then it looks like you burn for 35 seconds. So I guess I'm just going to assume that you burn for 35 seconds. So not main engine, like Seco. I'm going to do T2 end because I'm not sure if there's like a number. Anyway, I'm going to do T2 start plus 35.0 seconds. Okay. So now what you should be able to do is you should be able to say like, okay, if T is greater than T2 start, okay, that looks good. But, and T is less than T2 start, no, T2 end, right? Because those are absolute times. I already converted that in there. Then I'm just going to assume, so the one thing is I want to angle my, the angle of my thruster is there. Here, theta doesn't matter, so theta is just 0. Here, same thing, theta doesn't matter, so it's just 0. In here, I'm actually going to make theta 90, right? Because I want to fire sideways. Okay, and my thrust F, I'm just gonna say it's my max thrust. So then my m dot is negative thrust F over VE. Okay, and I think that's it. So I don't need to angle my thruster. I still need to make it 0 though. So if T is greater than T2 end, theta is 0, it doesn't matter, and thrust F is 0, and m dot is 0. We're not going to drop the second stage, we're just going to coast. And if we're lucky, we did not make it to orbit. What happened to our mass? All right, so we burned all of our propellant. So we can't, how long can we burn for? Or the other thing is that we can do here is drop less mass, right? So we dropped a ton. Let's drop like, I don't know, 0.2 tons. Okay. Yeah, it still didn't like it, so we're burning too long. Let's just burn for like 5 seconds. Let's see if that's okay. All right, so that's okay. But we definitely did not make it to orbit. What we can do is, this is ISP1. Let's make like an ISP2. That would change our exit velocity, wouldn't it? Crap. All right, so let's make a very, very efficient engine. So here's my exit velocity. So I'm going to need to compute my exit velocity every time, unfortunately. So that means down here, where I computed it, I've got to grab it and throw it up here. So here, this is going to be ISP1, because this is the first stage. That's where we drop the first stage. That's fine there. And then here, this is going to be ISP2. Okay? So we have a much more efficient engine. And I mean, we're at 2,000 kilograms. Like, we can burn longer. So let's just go slow. So let's try 20 seconds. That's not slow. Oh, dude, I think we got to orbit. We totally got to orbit. And we still have mass. So we are good. This is really cool. Look, you can see the first stage burn, and then burnout, coast, and then we fire again at apogee, and that's our altitude. So we just need to simulate longer. And then I think we have our 2-stage rocket. So our period is 500. Let's borrow this code here. Here we go for the period. And let's Control C that. And let's see. So I think I'm just going to make up R0. So do I still have my figures? What's my altitude at apogee? So let's say 200,000. So I'm gonna say my R0 is 200,000. So that's 200,000 plus R planet. By the way, remember we're on Kerbin. So there we go. So we definitely fired too long. So we can probably fire for like, let's just try to fire for like 10 seconds. Oh boy, we didn't fire long enough, and we went in the planet and then came out, and then went in the planet again, and then came out. This is actually really cool. I kind of want to simulate longer. How long was this? Like 3,500 seconds. This is kind of cool. Let's simulate for like 6,000 seconds and comment that out. This is really neat. This is like a lesson in, this is so cool. If you could go through Kerbin, this is what your orbit would look like. This is so freaking cool. I did also make the acceleration 0, so this is like kind of like not true. I think there's an if statement in the gravity model. If I said if r is less than 0, which is impossible, now our orbit should probably look drastically different. That's a Keplerian orbit. Yeah, that makes more sense. So technically, like in real life, you would crash into the surface, but at least in this case, the focal point of this orbit is right here, and it's twisted because I fired at an angle, and so technically the foci is a little bit different. I think that's called the argument of the perigee. I think I have a video on the orbital elements that you can go watch if you'd like. But anyway, basically, you just kind of go in here, but in real life, you would just crash here. So this just means I need to burn longer. So 20 seconds was too long. Let's just do the bisection method and try 15. 15 is not long enough. So halfway between 15 and 20 is 17.5. We're just going to do the brute force method. And there we go. I'm probably in the atmosphere here, so it would be neat on the next video, I guess maybe tomorrow, to add aerodynamics and see if I would actually still collide into the planet because of the atmosphere. But at this point, I'm satisfied. Let's look at these plots. Basically, I burn my first stage, I coast. When do I drop my first stage? Is it just like you can't really see it? Yeah, there it is. Well, yeah, there it is. You can't really see it, but yeah, I drop my first stage right there, and then I coast, and then I burn my second stage, and then I don't drop my second stage. I just keep it. Let's see here. So right here, I burn my first stage, and then I coast. And so I lose velocity because I'm coasting, and basically you're trading kinetic energy for potential energy by like climbing in altitude. And then I burn my second stage, and I'm going fast enough to essentially stay in orbit. And then basically you get Kepler's third law, which says that when you're at perigee, you're the fastest, and when you're at apogee, you're the slowest. So there's that plot there. Oops, I'm sorry. And then here's my altitude. So looks like I'm always climbing, right? So, I mean, I burn, I coast, and then right when I hit apogee, I burn again. And then at that point, I just do this oscillatory motion. So there you have it. I really hope you enjoyed this video. This one was really fun to make. I'm going to go ahead and just, because this code is a two-stage rocket and you have all the other versions, I'm just going to delete the other ones. So all I need to do is add in aerodynamics, and we're good to go. So post in the comments if you have any questions, and I guess I'll see y'all tomorrow. If I can get to the video, I'll try and post tomorrow. I hope you have a good night, and talk to you later.